Hello and welcome back to another lecture from organic chemistry. I want to talk about hemiacetal. And now we said hemiacetal is an intermediate that we get it whenever we try to take a carbonyl group in an aldehyde or ketone and try to transfer it to acetal. Okay, and hemiacetal are not that stable, and because they are not stable, you're not going to have much chance actually to separate them. And between the reactant and hemiacetal, there is equilibrium, and the equilibrium mainly is favoring the reactant. There are good reasons behind it, and we can start talking, start talking about the delta S and delta H of the reaction. And so I can say this. The way I get hemiacetal, I take a carbonyl and I will add it to 1 mole from an alcohol. So we have 1 mole ketone or aldehyde plus 1 mole of alcohol. That's going to give us 1 mole from product. And so until now, I'm going to say change with number of mole. We have only 1 mole from product, while we started with 2 moles from the reactant. So the change with number of moles, it will be -1. That means we paired 2 molecules and we got only 1. And because we forced them to get paired, I'm going to say change with entropy of the reaction is going to be negative. So let's write this. Delta S of the reaction until now is negative, which is bad things. That means the reaction does not want to go to that side. That's against the thermodynamic rules. But the thing that is happening, we are taking a pi bond and we transfer it to a sigma bond. Delta H of this process is negative. That means it's exothermic. We know if delta G is a negative number, the reaction will be spontaneous. And the question is, what's the delta G? Delta G is equal to delta H minus T delta S. The first term is negative, which is a good thing. Good to have the negative delta H, but delta S is the problem because it's negative, and negative multiply a negative sign here is going to give us a positive term. If minus T delta S happen to be bigger than the delta H, which is negative, then delta G it will be positive and the reaction will be non-spontaneous. So thermodynamic is saying that it's not surprising thing that reaction does not want to go to the right side, and in fact it's favoring the reactant. Now, between hemiacetal and acetal, and this time it's hard to say what's going to be the delta S of the reaction because we are taking 1 molecule, we add it to an alcohol, or alcohol to that's a hemiacetal, and that's going to give us acetal plus water. So I can say I started with 2, I got 2 molecules. It's hard really to judge what's going to be delta S of the reaction. You need more, you need to do way more calculation. And how about the delta H of the reaction? You started with alcohol, and alcohol, it has a 0 charge, and you got water. And again, you need to do some calculation to figure that one, to figure whether delta H, delta G is going to be a positive or negative. Here is a bit hard to really talk about it. There are some factors also involved, like a steric and electronic effect. For example, from hemiacetal to acetal, when we run the reaction, are we going to get a positive charge? Are we going to have an intermediate with a positive charge? If the answer is yes, then maybe you need to have something to stabilize that positive charge. Or no, if you get a negative charge somewhere, maybe you need to have electron withdrawing group to pull that negative charge, so then the system will be stable. But overall, when you form acetal, it will be locked in that position and it's not going to go back to hemiacetal easily. You need to, dilute it in acidic solution, and then it will go back. And remember that you have one product that is water, and you do have equilibrium, and the equilibrium is here. This is your equilibrium from hemiacetal to acetal. Okay. On other side of the reaction, we have water. If we take water out of the system, then the reaction it will move to acetal. Okay, so we can use this as a trick to get more from acetal compound. Now, and I said this one before, like from carbonyl to hemiacetal, the only thing maybe is changing, or dramatical change is going to be, pi bond is turning to sigma, and that's kind of like the driving force of the reaction. Well, we are taking a molecule with sp2 hybridization, we turn it to sp3 hybridization, and yes, sigma is stronger than pi, but also we are building steric effect. And so you have to include that one in your calculation whenever you're talking about the stability of the product versus reactant. Now, how can I make the system more stable? Our problem is delta S. If we make delta S, something close to 0, or let's say make it, positive, then that's going to be a good news. And you might say it's not going to be positive because you are pairing stuff. True, we are pairing, so entropy, it's going to get negative. But how about this? What if I can bring it close to 0, the change with entropy? In that case, yes, the reaction might move to the right side. How do we do that one? Okay. Now, instead of taking an electrophilic center, which is carbonyl, and like an nucleophilic center, let's say anything that is bringing actually a lone pair, like an OH, instead of using 2 different molecules like an alcohol and carbonyl, let's put them in 1 molecule. So we will have intra nucleophilic addition. Okay, oxygen of the OH, it will go after the carbonyl, and it will be added to the carbonyl center, and that's going to give us a ring. Now, if you run such a thing, and because you are getting a ring that it has 6 atoms, or 6-member, thermodynamically forming a ring with 6 members is favored. That's like it's going to happen, and it's it's not impossible. Yes, entropy is not in favor, but overall you're getting a stable system. And why? Because you took a pi bond and you turn it to sigma. So that's going to be a good driving force. Well, your entropy did not change a lot. And nature figured this one way before actually we figured anything about such a reaction. And nature managed to make, cyclic sugar molecules or carbohydrate. And through that one, first we can have, we can have a stable structure. And so it's not going to go through plenty chemical reaction. Why? Because anytime you have open or accessible, carbonyl group, that's going to be a weakness of a system because it has a pi bond. So it means it can go through some, unwanted chemical reaction, and that means it can transfer to something else. And the molecule managed to do like an intramolecular nucleophilic addition and get rid of that pi bond and turn it to, cyclic glucose molecule. So if we can turn the molecule, to cyclic, in that case, we can actually have or isolate the hemiacetal molecule. And I need to highlight the hemiacetal when it comes to the glucose molecule. We have an we have an OH or alcohol that is attached to a carbon that is already involved in interaction with another oxygen that is ether, actual functional group. So I have alcohol and ether at the same time. So I'm going to say this center or that carbon is going to be hemiacetal. Okay. Still, we have OH, it's not ether, and that's the reason I call it hemiacetal. Now, if you look to the linear sugar molecule, I'm talking about linear glucose molecule, it has one functional group that is aldehyde, and the rest are carbons with OH groups, and like some of them on the right, some on the left, and that's going to change entire the absolute configuration of each of those carbon. Are they important? Does it matter where to put the OH? Absolutely. And then I should say 100% yes, because entire of the chemical reaction in our body will happen in a way to to technically respect the configuration of each center. Now, this sugar molecule, because it has aldehyde functional group, we call it aldose. Aldose is technically talking about the sugar molecules that they have or carbohydrate molecules that they have aldehyde functional groups. You can use ketones whenever the functional group is a ketone instead of aldehyde, but in this case, it's aldose molecule, and that's an open chain. Look to the percentage of it. Only less than 1% of the glucose can be found in linear actually shape. While the majority of it is in a cyclic version. And the cyclic version, it can be in beta version or alpha. Beta is 63, while the alpha is 37. Now, what's the difference between an alpha and beta? Look to the hemiacetal center here, and next, highlight position of OH. Okay. If OH is taking equatorial position, in that case, we say is a beta, beta version, and if it's taken in axial position, it will be alpha position. So we have two isomers. The only difference between them technically is position of the OH group, and the equatorial versus axial. Axial, we call it alpha, and equatorial, it will be beta position. Okay. Now, these two sugar like any sugar molecule, it can actually see another neighbor sugar molecule and might have interaction with it. Okay, and so we have a cyclic sugar molecule and alpha glucose that is in equilibrium with a beta, and I want you to zoom on this side of the molecule. The difference between them, only position of OH for alpha is pointing down and beta is pointing up. Okay, now in beta, OH is closer to the CH2OH, while in alpha is far from it. And another part of the molecule that I'm going to highlight is carbon number 4. Okay, this is carbon number 1, and then 2, let's say 3, and that's number 4. Okay, so carbon number 4, it has OH, and that OH, it can actually do some interaction with OH that's sitting on carbon number 1. Now, imagine you have two you have two alpha molecules. Those two alpha molecules, they can reach each other, and carbon OH on carbon number 4, number 1, it can have interaction with OH from carbon number 4. Now, both of them are pointing down, and I can say, if I run any elimination reaction, let's say we take OH and H, remove them, that's going to leave us with one oxygen. Which oxygen? This oxygen. That oxygen, it will be bridged between carbon number 1 and carbon number 4. So technically we get an ether, but we are taking water out of the system. So I'm going to say minus H2O. I can repeat this one with with OH from let's say number 4, and H from carbon, the alcohol functional group on carbon number 1. But it's sitting on the, it's pointing up. So this time I'm going to say, take one from here, and then we go there. Okay, we eliminate those two. Okay, so it's difficult. Take those two out of the system. Again, we will get an ether bridge between carbon number 1 and carbon number 4. Okay, let's write the reaction. Okay, so I said one way we can bridge this. We can take those two. If we take those two, then we will get such a bridge. Okay, I'm going to show it like O attached to this carbon. Okay, so both of them are pointing down. And this corner is not a carbon atom. It's just a way to show that, both, OH, they were pointing down. Now we bridge them, we attach them, and now we, technically we build the etheric, bridge. Another one, if I take these two, forgive me. Bridge is going to be something like this. Put oxygen somewhere in the middle, then connect those two. Now, the top one, one of them is pointing up, and another one is pointing down, and that's going to give you 1 and 4 beta, so the 1 and 4 beta cellulose, and then interaction actually, or linkage. And my bad, 1 and 4 beta glycosidic linkage or bond. That's going to give you cellulose that we cannot actually process. That means our body is not capable of breaking this bond. And because we can't break that bond, even if it's a sugar molecule, it's a glucose molecule, we're not going to get any calorie from it. But our body is capable of breaking this bond. We can break it here, but there, now we cannot break it. The bottom one, we call it 1 and 4 alpha. Okay, 1 and 4 alpha glycosidic linkage, while the top one, we call it 1 and 4 beta. The beta is giving you cellulose, while the alpha is giving you starch, and we know we can process the starch and break it. That's really, really good subject, and it's a whole chapter actually that I can talk about it, but it doesn't fit in a short lecture video. So I'm going to start the lecture here, and thank you very much.